So the problem is the following. You have to boil water for tea. So what do? You take a kettle, you pour water, put it on a stove, turn on the gas, and wait till water boils, okay? So that's how physicists do this thing. Now, imagine the gas is already on. So what the physicists do, take a kettle, pours water, puts it on a stove, and waits till water boils. What mathematicians do, they turn the gas off, they say, we reduce the problem to the problem we already know how to solve. Take the kettle, put the water, put it on a stove, turn on the gas, and wait till the tea is boiling. Say it again, bad joke.
And Wojciech, I'm not a bad physicist, remember?
No, but this, and the funny thing is, but this joke was not told by the physicists. This joke was told by the mathematician. But anyway.
Stop while you're at it.
Okay. So now it's perfectly 10 o'clock. We can start. Okay. So I will be talking about really small scales in this lecture. So we went through So I have to acknowledge my people who really did the work. And there is a group of them. My colleague from the University of Warsaw is Hanna Pawlowska, who was involved with that. Hugh Morrison and Andy Wyszogrodzki, my colleagues from NCAR. Lianpeng Wang, my longtime collaborator from the University of Delaware. A lot of things that I will show in the second half of my talk will be definitely done by his group. And then two students, Joanna Slawińska, who is now at Courant, and Dorota Jarecka, who defended last summer and is still in Warsaw. So this talk really has three parts. But thinking what I should say, I decided to take out one part. So the work that Dorota did recently will actually not be shown here. It's just two parts then, because I prefer to rather go into some details of both of those parts rather than just quickly go to have it 15 minutes for each part. Now, you can ask the question, why shallow convection, or why boundary layer clouds? Why we worry about them? So that's kind of few points, and I will expand a little bit on just one of them. There is a good argument that these shallow clouds, examples are shown here, are really important in the climate system, and they play a critical role not only in the climate system, but in the climate change. And I will show some results that support that. The other point is that these types of clouds are where you may expect the largest sensitivity to microphysics. When you have very deep clouds with what we call large optical depth, microphysics really doesn't matter. There is so much cloud that what size of particles you have really doesn't matter. But in this intermediate range from clouds like that, when you change microphysics, you may reflect back to space more or less radiation depending on the changes. And final point is that if you think about approaches like superparametrization or even cloud-resolving general circulation models with grid lengths of few kilometers, these clouds will remain parametrized, till the end. In other words, even if you have cloud-resolving model with grid lengths of couple kilometers, these clouds will be really poorly resolved, or if they will be resolved at all. Now, about this critical role of shallow clouds, that's quite old diagram, but it actually illustrates the point very nicely. What it shows is something that is called double CO2 sensitivity. In other words, you run climate model with, let's say, current CO2, and then you run it with double CO2, and then you change, and then you look how the surface temperature changes. And among the models considered in this exercise, there were two models that have relatively large difference between the sensitivity. One is the NCAR model, and the other one is the GFDL model. And these two models, if you look at the changes in low-level clouds, show contrasting effects. The model which has largest sensitivity show that the blue colors mean negative change, and kind of warm colors mean positive change. So the difference in low-level cloud amount between, let's say, for the GFDL, you mostly reduce low-level clouds, whereas at NCAR you actually increase low-level clouds. And because low-level clouds reflect solar radiation and have relatively small impact on long-wave radiation, that kind of explains this range of sensitivities or model responses to the change in CO2. So that's the argument why we need to think about shallow clouds, because they do play significant role in climate change. In other words, whether the climate will change a bit or more may depend how these clouds respond. Yes, this is the third assessment. Honestly, I don't know. I don't think the picture has changed much. I think this is still a valid statement that the sensitivity between the models really depends on low-level clouds. And what I already said is that this resolving microscopic processes associated with those shallow convective clouds, but also with stratocumulus, requires grid lengths, let's say 10 to 100 meters, which means large eddy simulation. I will be talking about that in this talk. So, of course, this will not be achieved anytime soon. So when I talk about, when somebody talks about turbulence-microphysics interactions in those shallow ice-free clouds, so we're talking about warm clouds, such as tropical cumulus or subtropical stratocumulus, there are several issues that you may think of. One, of course, is turbulent entrainment, and we know what entrainment does to the cloud. We know that shallow clouds, especially cumulus, entrain a lot, and based on some bulk arguments, you know how much water needs to evaporate, but this water can evaporate in different ways. So that's one of the aspects that is not very clear. In other words, how the spectrum of cloud droplets changes, mean size or concentrations, and then you may think about in-cloud activation. I will be talking about it quite a bit. This is the part that I will actually that I decided not to talk about, the homogeneity of parameterized subgrid scale mixing. So those are processes that are related to entrainment. And the other part is that turbulence affects growth of cloud droplets and formation of drizzle rain. And that's the part that we've been working with Jan Peng for quite a while. And I have some really interesting and intriguing results that I will show today. So in my talk, I will be using two types of warm-ray microphysics. One is what we typically call a double moment microphysics scheme, warm-ray microphysics scheme that my colleague from NCAR, with my help, developed some time ago, and then we actually verified comparing to the bin microphysics. And the other one is bin microphysics that kind of has been around for a long time, but I recently worked to kind of improve it, especially the activation part, and I use it as well. So this double moment microphysics, you basically predict just few variables. If you think about cloud droplets and drizzle raindrops, you just use 4 variables of that. It's mass and numbers for these two categories. You also predict in-cloud supersaturation, which actually plays a significant role in what I will be talking about. There are double moment schemes that only work in a simplified way. They don't predict supersaturation. They assume that clouds are at water saturation, which is actually a pretty good assumption, but not if you would like to look at the details of activation. And then, because of the activation, you have one extra variable that you carry around in a model to basically eventually predict additional activation, if you like. And then, again, subject I will be not talking about is that in this double moment scheme, we have a very simple way of predicting those, including those various mixing scenarios. And actually how you do it is, well, if you want to predict what is the homogeneity, it's quite elaborate, and we have a paper that we just submitted on that. So this will be used in some simulations, but not all of them. For most of what I will be showing you is actually bin microphysics, and this is just the illustration, what bin microphysics means. It means that you're trying to resolve the size distribution of droplets, and this just comes from one of my simulations, basically to show that the particles smaller than 25 microns, you may think about this as cloud droplets, and whatever is larger, you call it drizzle or rain. And these are just in two different parts of a cloud. In this part, there is some cloud water, and this is just drizzle and raindrops. So this is, of course, much more computationally intensive, because if you would like to represent this spectrum with some fidelity and processes that lead to production of drizzle raindrops, you need quite a few variables. In simulations I will show, we use 112 bins. And you also predict supersaturation, and then you relate the concentration of droplets to the activation. So you need some method to activate droplets, and I will not talk about this in detail. So that's kind of a general kind of framework description, if you like, that I will be using throughout this talk. Now let's start with some observations to kind of position ourselves in terms of what kind of microphysical processes we expect to see. These two come from two different papers, but from a relatively recent project called RICO, Raining Cumulus over Ocean in the Caribbean 5 or 6 years ago. And what this figure is aiming to show is that if you go high, and I need to explain, those are basically some flight levels from near the cloud base to going higher up. So the height, if you like, goes down in this figure, and this is more conventional representation where height actually goes down. So let's first look at this table from Gerber's paper. What this figure, those kind of highlighted columns in this table, what it shows, this column shows the adiabatic liquid water. In other words, the amount of water that you would expect to see at that level if you just take a parcel from the cloud base and move it up. So it changes from about maybe 0.6 gram per cubic meter to 2.5. Now, the actual mixing ratios are, as you can see, much smaller than that. They range from maybe 20-30% lower down, 20% higher up, down to maybe 10% near the cloud top. And then this column shows the droplet concentration. And then what you see is, despite this dilution of a cloud, the droplet concentration is not decreasing at the similar rate. It's actually increasing, and only near the top, when the dilution is really strong, you see that the concentration goes down. And I have to explain that these are not single clouds. These are, in RICO, basically the aircraft flew long legs targeting many clouds. So these are basically cloud statistics. Those are just mean values. This paper by one of Hannah's students, shows it in a different way. It shows basically distribution at different levels, and of course the aircraft didn't fly at all the levels, so that's why you get kind of a patchy pattern, if you like. And darker color shows the more frequent values, and then you probably cannot see it, but there's also a bar that shows the median, but it's kind of somewhere here and then somewhere here. So you can see that, for example, for on that day, these are just different days, several hour-long flights of C-130. For example, here you clearly see that the most frequent concentration increases, and the other thing is that it actually varies quite a bit. The variability is large. So these are observations. Now, the model setup that we will be using is the Barbados BOMEX case, Barbados Oceanographic and Meteorological Experiment, which basically has prescribed profiles, 500-meter deep subcloud layer, the convection layer about kilometer deep. Of course, clouds sometimes penetrate, and they do above, and then trade with inversion and wind and profiles. And this is just the example of kind of how these fields may look like. Cloud field, you have several clouds, basically clouds going through their life cycles, and you run it for several hours, and then you gather statistics. And this is example of model results, which basically supports what I already highlighted in the observations, that if you run the model, this is the adiabatic liquid water that you expect to see, but in reality you see the cloud water somewhere within this range. And this is actually from set of different models, comparing different models, LES models, and the envelope of those different mean cloud water profiles is shown by this gray. But the point is that basically, like in the observations, we see that there is a very significant reduction of the cloud water mixing ratio with height. And of course, RICO is not the first experiment that showed that. This is known for decades. several decades, going back to early cloud observations in the 40s and 50s of the last century. So that's nothing new. However, you may ask the question, how is possible that the dilution of cloud water is not accompanied by the dilution of cloud droplet concentration? In other words, when you dilute the volume, how come that the droplet concentration doesn't change? And of course, the very simple answer is that there is probably activation above the cloud base. And again, this was also hypothesized in some of the observations, but I think now on the modeling side, we have a really good proof, if you like, of that this is really what's happening. So using this BOMEX setup and bin microphysics in this case.
May I ask, sorry for this, what do you actually mean by activation?
Well, this is how you create droplets. Droplets don't come around or about just from nothing. You get cloud condensation nuclei which you activate near the cloud base. Okay? So in other words,
Are you talking about only non-raining clouds?
Well, this particular case is non-raining, but I will move to rain in about 5 minutes. Okay? So I'm talking about now only about clouds that do not precipitate. So all those simulations here are without precipitation. No. Are you asking about rain or asking about cloud? No. Wait a second. Let me continue. Maybe this become clear. So
what you've done is you've cut off the activation in your code.
Well, so what I've done is, so basically there are two simulations here, just snapshot to show you what I mean by activation above the cloud base. So one simulation has activation always on. As you can see, you have a lot of activation near the cloud base. That's where the air...
The nuclei, the water and all of it.
Yeah, so we get cloud condensation nuclei in the air, and when it's moved through the cloud base, supersaturation builds up. I don't want to go into those details, but basically that's kind of the physics how you create cloud droplets. Say it again? Well, that's you can define it where the cloud water goes above some threshold. Well, it doesn't matter if I change my threshold from 100 to 1,000 gram.
What threshold?
Well, I don't remember. I mean, you're asking relevant questions because you will move 10 or 15 meters. It's not the point, but you can see where the cloud base is here, and that's a 3D picture. Just look from the side. So this. So basically, I will show. Anyways, it's the layer when you activate. In clouds, it's typically 20 to 50 to maybe 100 meters of depth when activation really happens. And in this simple picture, when you have a parser going through the cloud base, you add droplets, and at some point you stop because supersaturation begins to go down because you activated enough. So now they're just growing. Okay? So this depth is few grid points in this simulation. But anyway, so this, you see with these dark colors that there is also a lot of activation above the cloud base. Okay? Now, you can say, okay, I don't allow activation above some height, let's say 700 meters. The cloud base is about 500 meters here. So you just allow activation at the cloud base, and then you do not allow it above. And then, if you look at if you just conditionally sample how much activation you have, so of course in the simulation when you don't allow it, it's just cloud base and nothing there. But here, it's actually quite a bit. And if you do actual calculations, about 40% of cloud droplets in those small, shallow clouds are activated above the cloud base, not at the cloud base. So these are relatively low-resolution simulations. Before I say that, let me show you this figure, which is just the droplet concentration plots. So this comes from the bin microphysics. Again, this is activation not allowed above 700 meters. This one is activation is always on, and as you can see, and these are just percentiles of the droplet concentration. So the mean concentration increases with height. Here it decreases with height. The more dramatic effect actually comes when you consider double moment microphysics scheme, a simple scheme, so you can run it longer, for example. You can run more simulations. So don't worry about those 4 panels here. They are just different microphysical setups, if you like. But the key point is that if you turn activation off above 700 meters, then your concentration dramatically decreases with height, and the mean increases a little bit, and there are some reasons why you see that. Whereas when you keep activation on, it basically increases with height. So these results, both from double moment microphysics and from this bin microphysics, show that you really have to allow activation above the cloud base. You may ask how this activation happens, and we actually did some work on that long time ago, 20 years ago, with my French colleague Jean-Louis Branguet, in a model, slightly different bin model, but it's also a bin model. In other words, you look at the spectrum of droplets, but the setup is slightly different. So what I'm showing a small cloud which has this toroidal circulations near a cloud top. Of course, this is in 2D, so it's actually a vortex pair, if you like. This figure just showed that the circulation, as you kind of expect from this figure, goes like that. And this, again, the same size and large here. And this is really crazy diagram because in each grid box you're showing a small droplet size distribution. On the next slide, I will have this part expanded. The point is that the air kind of goes like that. So there is some evaporation of water here, and then it comes back and gets activated again. So in other words, you have an updraft here through the main part of a cloud, and then it kind of circulates. And that's where this entrainment event, if you like, if you want to call it like that, happens. So the air that comes here, of course, activates new droplets. And this is better represented. This is just this part where the air comes in, enlargement of some of those droplets. And you can see that there is, besides this kind of a peak of droplet spectrum somewhere here, there are new, freshly activated droplets. So you, in other words, in this part of the cloud, you see the bimodal distributions, as we sometimes call it. In other words, you have this mode at larger droplets that is associated with droplets rising from the cloud base, but you also get newly activated droplets that are activated on the cloud condensation nuclei that are entrained. And the additional point that one can make is that those CCN cloud condensation nuclei that come here, they not necessarily come from the far environment. Some of them is basically already processed through cloud, comes out, droplet evaporates, and activate again. But of course, this leads to this bimodal distribution, which in a bin model you can simulate that. But of course, in the double moment microphysics you cannot, because you always assume that there is some shape of a spectrum, and this shape is not double peak, which is perhaps a caveat not relevant here. So basically, the kind of conclusions from these couple papers, the simulations, is that we quite often, especially in terms of cumulus parametrization, people tend to think that you get cloud-based activation, and then basically they don't really solve the equations that describe the transport, but they basically say whatever is activated at the cloud base is representative for the entire cloud. And that's certainly true, but physical mechanism is that you activate at the cloud base, but you also activate when you entrain.
So in nature, though, the number of condensation nuclei available, how do they vary with height?
Well, that's a very good question, and it really depends. In some environments, it varies not much. Like, for example, for the convecting layer within the subtropics, you don't expect to have much variability because you keep mixing. But in over continents, and I think Tara had some results showing that it can really dramatically. Yeah, it can really degree.
Dust over land that gets transported.
For example, yes, and of course. Yeah, and you have to be careful because of course dust is not good CCN. So.
Yeah.
This is ice nuclei is dust. Yeah.
So that is an input parameter, isn't it? Nuclei and
Yeah.
So you can vary that. It's under your control and make the simulation.
Yes, and I will show you. I'm going now to the second part, and it's going slower than I thought. So.
I have one comment on that.
Okay.
The second one there. I'm sorry.
Oh. Sorry. What happened? I just. No. I basically pull out the plug. Say it again. Yeah, so there is, of course, I mean, this is part of the eddy, so there will be air that comes out, they evaporate, And there is actually a shell that goes near the cloud of the air descending, and it's model in observation is there. So that's what I made the point, that you not necessarily bring in the air that is from the far environment and activate. It's a mixture of what's going on further away and what is already in a cloud, if you like. So it's really, really complicated process. But I.
Actually, the traditional view, it is in cases like this, like active cloud, for example, it is more similar to the traditional view than the other.
Well, I mean, I don't know what traditional view is. I'm telling you, well, okay, so that's a time. But this is from the point of view of convection parameterization, when people say activation only happens at the cloud base. And then, as long as you assume that this activated at the cloud base for those shallow clouds is pretty much constant with height, that's okay. But then on the other side, on the thermodynamics, you assume, strong entrainment. So how you can, so that's basically the physical mechanism that lets you escape. We never get to the end, by the way. And the end is very exciting.
Okay, so let's get
It depends on what you mean by the traditional view. If you take the view that was very common in the 1960s, 70s, it was this view.
No. In 1950s and 70s, people didn't measure well droplet concentration.
I'm talking about the fluid dynamics.
Well, fluid dynamics, there is no. Well, fluid dynamics, on the fluid dynamics side.
Combustion people would take the view on the right. All the combustion people.
Well, but let me tell you, what you're thinking. You're thinking about the entrainment. You think?
I agree with Rob. All the combustion people.
Yeah. But you see the. But you mix into things. There is. Remember, there is also entrainment in the traditional view. I'm not questioning the view of entrainment, because we know that clouds are diluted. So I'm talking what happens when you have entrainment. The traditional view is there is a cloud dilution, obviously, because we know this from observation. But what happens with droplet concentration is unclear, because you can either, if you just assume that you dilute the cloud, that the concentration should go down, but it doesn't. And why it is so is because there is entrainment and activation. So the entrainment is there in both pictures. This traditional or this new, if you like, view only concerns activation of droplets. It doesn't concern the entrainment part. This is the same. Okay?
So is it basically just because the lateral entrainment, you typically don't get as large of a supersaturation, so you won't be activating as many droplets?
So basically in this model that I show you results here, the air comes in, and what happens here is kind of similar to what happens at the cloud base. It's basically new.
Right, but you don't generate as large of a supersaturation.
Well, it just depends. It depends on the vertical velocity. So if the vertical velocity here is larger than here, you will activate more. But on average, it gives you pretty much constant or maybe slightly increasing concentration. Let's leave this behind. Let's accept the view. Let's don't read the conclusions because we discussed them so much, and let's go to the next part, which is really exciting, because it's my work now over a decade with my colleague from Delaware, and it's the question what turbulence does to the growth of droplets in general, and specifically for the collisional growth. And if you think about a small box, kind of like that, and turbulence in this box, and you follow position of droplets, and this is just one slice, if you like, and droplets that are in this slice, you may certainly think that if you get droplets that are in this volume will grow in a different way than droplets that are in this volume. And that, you may argue that this should apply both for growth by condensation, but also for the growth by collisions. And I will be talking mostly, about the collisional growth, and the argument why it doesn't play much role for the diffusional growth is that this is just a still picture. If you would look at this picture 1/10 of a second later, the droplets will rapidly rearrange. So in other words, if you think about condensational drops, these two lucky drops that don't have neighbors and will suck water vapor from here, perhaps have higher supersaturation locally, and here supersaturation will be lower. You look a second later, and these droplets may end up in a cluster like that, and these droplets will be dispersed. So, in other words, condensational growth is reversible. When you are lucky one moment, you may be not lucky later moment. Collisional growth is different, because if you get a collision here, that's an irreversible growth. They collided, and now they will be just one new droplet, okay? So we're looking, and we actually quantify that there is insignificant impact on the diffusional growth because of the reason I explained, but there may be quite significant impact on the growth by collision coalescence. I need to start moving faster. So over the last 10 years, we developed what we refer the turbulent collision kernel, because most of what controls droplet growth is basically gravitational growth. And that's the traditional textbook way of cloud droplets growing in a cloud, from cloud droplets to drizzle, eventually to rain. But when you get turbulence, the picture changes. And through these DNS simulations following thousands and millions of droplets, Lianpek came up with a way of deriving some enhancement factors for the collisional kernel. And this is what this figure is showing. And the parameter that controls this is the eddy dissipation rate. So these are, because of course kernel is symmetric, so one half of this diagram shows enhancement for the lower, the second half shows for the higher, and of course you may ask, what is this line in the middle? Well, of course, for collisional growth, for gravitational growth, when you get the same droplets, the kernel is zero. So of course on the diagonal, when you collide one droplet with the same droplet, the enhancement factor goes to infinity. Now, what the circle is showing is basically the relevant range of droplet sizes between 10 and few tenths of microns. And as you can see, somewhere here, away from this diagonal, you can see the factors of maybe 1 or 2 for 100, and maybe 3 or slightly larger for 400. So in other words, the collisional kernel, and it also includes effects on collision efficiency. Collision efficiency is basically hydrodynamic interaction when larger droplets approaches the smaller one. At the very end, they will interact hydrodynamically, and the small droplet may basically go around the large droplets. And this is, of course, a very difficult problem in the simulations that Jan Ping was doing, because this interaction happens over small distances, maybe a fraction of the droplet radius, so you can 10 microns. So to resolve it, you would need to use a grid of maybe a micron or 2, and you want to do a DNS of as large box as you can have. So he actually invented a very nice of doing it, relevant, I would say similar to superparameterization, splitting the problem into two parts, one dealing with hydrodynamic interaction, you can treat it as a Stokes flow, and the other one doing basically turbulence on a larger box. So these DNS simulations guided development of the turbulent kernel, and what I'm showing here is basically the end product. This is what goes to the model. Now, just to demonstrate that it really has a significant effect, what we're looking at is the droplet size here and rate of change of the droplet mass distribution as a function of time. So these different lines, and time goes up. So what happens initially, you have small droplets being collected by slightly larger droplets, and that's why you have a kind of dip down and dip up, and this lasts for a while, and eventually the peak at larger sizes, more into drizzle, shows up. This first phase is traditionally called the accretion phase, and then this is, autoconversion phase, and then you have accretion phase when you already have some drizzle, and drizzle collects those small droplets. And then it's basically what is called a self-collection. In other words, those big ones collecting smaller ones. But what this figure shows is basically when you have no turbulence, this is a classical picture, and the time here is about 15 or 20 minutes. When you add turbulence, and this is quite vigorous turbulence, as you can see, this autoconversion phase, in other words, the time that you need to produce first drizzle is significantly cut. In this case, it's cut by half. Okay? So, and this is a very simple experiment. You basically take a spectrum of cloud droplets and you solve Smoluchowski equation that basically describes the evolution of the spectrum, okay? So we are still a little bit away from kind of realistic clouds, right? But knowing this kernel, we can use it in realistic cloud simulations, and again, we will be using Bomek's case. Now, before we do that, we need to consider one extra factor, which is that there is a gap between LES and DNS. In other words, if you think that this is your larger dissimulation box, 10 to 100 meters, you can have a lot of DNS boxes, if you like, and because DNS was guiding development, those turbulent enhancement, you may ask whether the mean dissipation rate of a disk box, of course, will be, it has some distribution because some of those, you may think about this as the intermittency problem. In other words, the mean turbulent characteristics over this large box translate into highly variable characteristics over collection of those boxes. So I will skip that part, but we basically show that situation is not as bad as one would imagine. The correction factor is close to 1 for those effects. So I think this is also an interesting result, but I will not discuss it in any detail beyond just saying that we included this intermittency effect. Now, because as was already commented, the rain formation really depends on concentration of cloud droplets. We consider a concentration of cloud condensation nuclei. We consider a range. So in other words, we expect that in this really very, very clean cloud environment, we expect to have more rain than in this one. And the formula basically is very simple that we use in a model. It basically limits the number of droplets activated if the supersaturation is larger than 1 to the number of available CCN, and it really doesn't matter how this is done. It's just to tell you that we consider a range, and these numbers tell you the maximum concentration you expect. Now, before we go to the cloud field simulations, I did a couple of very simple simulations that actually illustrate very nicely what kind of enhancement you may expect. And it's a very simple setup. It's basically a two-dimensional bubble that rises. So you have a temperature perturbation, water vapor perturbation. It rises in the stratified environment, produces clouds, eventually produces rain, and rain falls out and gets to the surface. And for the reasons that will become obvious later, let's consider two situations. In one, the bubble rise is stopped by the inversion, okay? And the other one, the bubble can rise really unobstructed, and it becomes obvious why I chose these two. And let's assume, okay, normally you would expect that, of course, in different points you would have different dissipation rate. But just for the sake of argument, let's assume that in all cloudy points you have a constant dissipation rate. And of course, the idea is that you will run gravitational case and you would run this turbulent case and compare the results. And the next slide will actually explain why I'm using this kind of perhaps a little bit elaborate way of explaining results. So in this case, when you get inversion, what happens, the cloud rises, hits the inversion, and the rains form and falls down. Okay, so I don't have similar picture here, but basically this cloud will not look like that. It will be basically a collection of smaller thermals. One just breaks into smaller parts, basically rising up and rain falling down. Now, here what I'm showing is, first of all, is the center of mass of the condensed water. And I'm using this to basically tell me what cloud is doing, how it behaves. It's for the one variable when it rises. So in those two simulations, both behave like that. In other words, cloud cannot rise anymore because there is an inversion here. And then, of course, the center of mass kind of begins to oscillate near the inversion. Now, what is interesting to see in this case, that in the turbulent case, you get significant more rain, but also rain forms earlier. The fact that rains form earlier is not surprising. This is what this previous simulations, I showed you that autoconversion starts earlier. So few minutes earlier, you get rain at the surface. This is rain accumulation at the surface. But more surprising is that you actually have more rain. And you may think why it is so. And the simple explanation might be that if you form rain earlier in the life cycle of the cloud, because this is just a snapshot, this cloud will kind of dissipate and rain will stop. If you produce rain earlier, then you have more water to collect throughout the life cycle. So this is how you get this maybe 40% enhancement. Now, if this bubble rises without any problems, without any disinversion, then it's very interesting because, as you can see, the turbulent bubble rises a little bit faster, and especially towards the end, it actually goes to much higher levels. And then you may ask why this is so, and the explanation is very simple. If you think about the effects of condensation and loading of water that the air is carrying with it on the buoyancy, once you have rain, the rain falls out from this parcel, and the bubble can rise faster and reach higher levels. Okay? So that's basically what happens here. And if you look what is the enhancement in this case, is dramatic. It's factor of 2. So what you can think about is that this simulation represents what I would call a microphysical enhancement. In other words, cloud dynamics behaves the same. You just have 40% more rain because of microphysical consideration. Now, this case actually it should say microphysical plus dynamical, because of course microphysical is still there, but you also have dynamical enhancement. In other words, cloud can reach a little bit higher up because you take out this negative buoyancy due to condensate that you're carrying with and dump it as rain. So clouds can reach a little bit higher, and that's why you get factor of 2 enhancement. So of course what we do, we run a BOMEX simulations again, and as I said, we run it with the range of concentration. This is just a snapshot to show that you get clouds at different stages of their life cycle. Some of them precipitate already at the ground. Some of them just begin to precipitate. Some probably will never precipitate. Some are just remnants of old clouds. I will skip that, and I will go straight to the results because I should finish within a minute, which will not going to happen, I can tell you that. Because the most interesting is still in front of us. What we're looking here is the domain average evolution in time, so time goes like that, evolution of the domain average cloud-water mixing ratio. So in other words, and this is for those different simulations, this one which is easy to produce rain, this one which is more difficult to produce rain. And as you can see, it's basically very noisy, if you like. It's not because the cloud field pulsates, as you can see, there is what those streaks mean, that there is more cloud water at this time, and of course these clouds are growing up, so that's why you get those kind of streaks going up. So this is your cloud base. Now, there's also some cloud water, and the cloud water, again, is defined by dividing the spectrum and integrating over just parts of the entire spectrum. There is some cloud water beneath, and this comes from evaporation of rain. Okay, so this is just cloud water. This is, and as you can see, also there is, for some reason, there is more cloud water in some of those instances when you have turbulent kernel. So I should say, this is just gravitational kernel, this is turbulent kernel. So there is basically, 8 simulations here for those different concentrations, and then gravitational and turbulent kernel. There are some this is the CCN concentration, yes. So now you're, of course, looking, what about rain? Okay, so as expected, there is very little rain leaving the cloud for those high CCN concentrations. There is quite a bit of rain leaving cloud at this low CCN. Okay, and again, there is this kind of pulsating nature, obviously. And then if you put say it again. Yeah. So model is exactly like, we do any trick with activation. You activate when you need it, when you activate. And we actually check that those profiles, whether you have rain or not, look quite similar to those profiles that I showed earlier without rain. So the fact that you have rain doesn't have dramatic impact on droplet concentration. It has some on other things, but not on droplet concentration. So so now I'm putting them together because now you can see that these ones produce very little and this one produce more. And more interestingly, if you just look for some integrated measure for those different simulations, maybe liquid water parts and rainwater parts, in other words, integrated in a vertical, something interesting shows up. For when there is no much rain, there is very little rain in this case, so let's leave this alone. But here you can see that there is no much difference between liquid water parts. So this is this wiggly line is the evolution, and the solid lines are basically averages from 1 hour to hour 6. When you have rain, you can see this dynamic enhancement. Not only you have more rain in those cases when there is rain, but there is more water in clouds, and it's kind of intuitive, because more water means that more rain means that you've taken some water out. But nevertheless, this is the dynamic enhancement. You have more water because clouds are slightly deeper. Okay, now, so that's what I was just said, that this is microphysical enhancement. Here you basically see a little bit of enhancement of surface of the integrated rain, but clouds are the same, whereas here you get, between this, again, gravitational and turbulent kernel, you get more cloud water and also more rainwater. This is perhaps the most interesting figure. What we're looking at the surface accumulation rate. Yeah, I'm about done. I'm sorry about that, but the joke took 3 minutes. So this is the evolution of surface accumulation. In other words, how much rain you have at the surface. And as you can see, when there is a lot of rain, you get factor of 4. When there is not so much, it's factor of 10. So there is really a dramatic enhancement from this cloud field. And I will skip a little bit of illustration that people done it in a much simpler model and came up with similar numbers. And I will stop basically saying that not only we are now at the stage that we can do those simulations with realistic turbulent kernel and NSS. And I have to stress, this is not a single cloud simulation. It's a cloud field simulation. So that's why that's a different than a single cloud, because all those feedback between clouds are there, and it's difficult to separate this microphysical and dynamical effects, but there are some ideas how to do it. And perhaps the last point is that there's really strong magnitude of this effect, and we really need to go to the field and look at some observational and then modeling studies to provide more support. And by observational, I mean remote sensing, because you need to look at the cloud fields rather than just fly through few clouds. So it's either satellite or ground-based radars to try to tie the depth of a cloud field, the droplet concentration that you have, and the amount of rain that you get out of them. And I think there should be enough satellite data or ground-based data that we can look. But the effect is really astonishing. I didn't expect to see such a big effect. Thank you, and sorry for a few minutes longer.
So you're using the conditional dissipation rate from the large scale as your parameter for you're using the conditional dissipation rate from the large scales as your parameter to parameterize your local process for cloud microphysics, the Smolchowski equation bin. So what I'm wondering is, you mentioned, so that's a very fluctuating, highly non-Gaussian statistic in turbulence.
Yes.
So I'm wondering, right now you have kind of a mean model. So how are you doing the fluctuations? You mentioned briefly what you were doing over the small boxes and going to let that fluctuate. How are you doing that?
I mean, how we came up with, well, so...
If you use the constant value, that's probably not good.
Well, you mean constant value? For each box has eddy dissipation.
Each large-scale box, you have eddy dissipation.
When you say large scale, what do you mean? LES scale?
LES scale.
So LES scale has local dissipation rate that comes from TKE.
Yes. Okay?
And that's the mean for this box. And that's what we're using for the collision kernel. However, in this part...
You don't allow fluctuations of that quantity over...
No, Andy, but this part of the talk was supposed to convince you that if you consider this aspect ratio between sizes of the box, and you use Kolmogorov 61 scaling for how it should scale, then you come up with not such a large effect. this is dissipation rate, this is this kind of correction factor between using the mean and considering those distributions. And as you can see, so including intermittency effect, that's how we kind of call it. And I think this is the only way you can actually justify what you're doing. So the things that you talk about, we actually include. Perhaps in a not perfect way, but we do.
Okay, so I see. I saw your left-hand picture of your slide.
Well, the left-hand picture is basically...
I know that was your diagram.
No, that's a different diagram. This is the same type of diagram, but it shows the correction factor for different droplets colliding with different sizes, given the mean dissipation rate and the ratio of the sizes. And this one is just for selected droplet sizes and different ratios. Sorry, I skipped too quick, but basically I was worried about those things from the very beginning, and this part analysis convinced me that we can actually do it. Yeah.
Well, it's very interesting that you're making the connection with rain, but I want to go to the condensation process. As I understand it, you start with cloud condensation nuclei.
Yes.
Put that in as input. They take part in the motion. Do they take part in the motion? They do.
Yeah.
And then, when the condensation occurs, you must therefore have, in your simulation already, a value for the amount of heat released.
Oh, yeah.
Latent heat released.
Yeah.
Now, could you tell me how much of what the parameters in your simulation are that need to be known before you actually compute the amount of condensation that takes place? You talked about the turbulent, the fine-scale turbulence.
Yeah, which doesn't have effect on the condensation. That goes back to something we discussed offline.
Yeah.
This is very complicated model, but you can build a much simpler model, basically assuming that cloud is exactly at water saturation. That's a model that dynamically will differ from the sophisticated microphysical model in real details. In other words, if you would plot, and I showed diagrams like that, if you would plot different droplet concentration, the difference, let's say, in the amount of water is thickness of the line that you plot. Because we're talking about supersaturation of, let's say, 0.1%. So that's 0.1% of the amount of water that you have. So
in other words, you're saying it's insensitive. Is that what you're saying?
Yes, that's what I'm saying. And you can actually do, if you're interested in the dynamics, not about those microphysical aspects that here we emphasize,
right.
You can build much simpler model, and Andy knows that because he built models like that as well. The assumption that cloud is always at water saturation is a very good assumption, and it simplifies a lot of things when you consider cloud dynamics. It's not very good once you bring ice processes, because then you don't know what saturation means.
Ice particles is a different thing. That's correct.
Yeah.
Mm-hmm.
Okay, there is one question, if that's okay. We have tea here, am I right? I mean now, am I right? Are we cutting into tea or are we cutting into somebody else's talk?
Okay, I have a question. Last but three slide or 4.
Say it again, which one?
Last but 3, slide number last, just before that. So this, or even before that maybe, just where you are showing the aerosol in different, So you are showing the different at different aerosol concentrations.
So these are aerosol concentrations.
Aerosol concentrations, and you have the evaluation of cloud liquid water.
Yeah, so that's on every level you average horizontally, and that's one point. And then you move to the next time step. So, for example, these are periods where there is more clouds, more rain. It doesn't mean that there is just one cloud that it's raining. So it's kind of domain average. I mean, it takes me a while to understand what this figure is showing. For example, this oscillations is just not the one cloud oscillation. It grows and decays. It's just that the field itself kind of, breezes. And that's because we know how clouds interact with the environment. They send gravity waves that stabilize the environment. So then, all those kind of processes between one cloud and its environment. So
yes. So my question is, when there is an activation of a nuclei, it consumes the aerosol, right?
Yeah,
and since this model is not interactive with this aerosol, so that when it activates, it doesn't decrease the aerosol amount. Do you expect a change in this simulation when you have an interactive aerosol concentration?
no, it's not entirely true what you just said. We have extra variable, which is the number of activated aerosols.
Exactly.
So it's not a bin on the aerosol side, but we keep track how much from this 60 or 30 or 220, how much is left and you can activate. And that tells you how much you have to build supersaturation before you start activating. So it's a relatively simple model, but it has some, I would say, reality, how we expect clouds to work. For example, you cannot do aerosol processing, or you can do it only in a very simplified way. In other words, having a spectrum of aerosols and droplets, and how then cloud droplet and rain and drizzle evaporate, because remember, each drizzle has thousands and millions of those initial CCNs, because you basically took everything from those millions droplets and put it into one. When it evaporates, it leaves one big aerosol behind. So those kind of feedbacks are not considered here. But some of the in-cloud activation, for example, this is, I would argue, done as quite well. I don't expect to have any problems on that. And that's actually why you get in-cloud activation in my first part, because you keep track of how you already used, and if you know about activation, which I'm sure many of you don't, the idea is that you can tie the maximum supersaturation at the cloud base. That's the amount of aerosols that you use. And if you keep track of this concentration that you activated, that tells you how far you have to go above. That if you go above this supersaturation at the cloud base, that's time to add new nuclei. So there is some relatively simple and perhaps for some complicated mechanisms to deal, but you cannot deal with all the complexity. Actually, to do it right, as many of you know, that requires two-dimensional bin microphysics, droplet sizes, aerosol sizes. So rather than having 100 variables, then you're moving 10,000 variables. Try to do that. Good luck. Good luck.
May I?
Tara has a question.
Actually, about the rain formation, turbulent effect on rain formation, it is correct to say that the collision coalescence efficiency may be enhanced due to the turbulence effect.
And that's included. That is included.
And in this particular case, we are seeing higher liquid water content with the turbulence, enhanced turbulence. That may be also because it is a cleaner case. And in a polluted case, for example, such effects are quite reduced because the collision coalescence effects are kind of suppressed.
Yeah.
Maybe because of that.
Yeah.
So the collision coalescence efficiency is the one that is.
Yeah, and it's these are really brand new results. We're about to submit the paper, and this is really kind of the tip of the iceberg. We just begin to understand some of those interactions, and of course the role of microphysics and then cloud processing. I argued in the first phase of my talk that the air that is entrained into the cloud has a lot of aerosol that already went through a cloud.
Yeah.
So all those things need to be considered, and what it does when you have clean environment, what it does to the polluted environment, what happens when you get dust particles which are coated.
Yes.
These can be actually CCN. We know that dust themselves, it's not CCN because it's not soluble, but you coat it with sulfates, and then you get good CCN. And then, of course, interesting point, you carry those tiny grains of sand, and they are inside the droplet already. You go to cold temperatures, they will be good, probably good ice nuclei.
I did some simulations also, and then came up with regarding rain formation, and also from our observations, we came up with a similar conclusion that collision coalescence is the one that is to be more.
Well, I mean, these are shallow clouds, no ice. You get much deeper clouds, so it's more complicated system, obviously.
But in the warm part of the cloud.
My suggestion is, let's go we have 15 minutes for tea, am I right now? Thank you very much.